Okay, so next up is Filippo Nuccio from Università Monet, and Filippo will tell us about analysis and functional analysis in Mathlib. Thank you.
Yes, so thank you, Marco, thank you, all the organizers. So what I'll like to do is more or less what Ricardo did, but more for analytic topics for the analytic part of the library. So I hope to get to functional analysis. It will not be sure, but for sure, what I need to start with is the way we treat limits in Mathlib. So for some reasons that I'll try to explain, limits are not treated in the usual epsilon and delta way. And so let's see what we normally do. The approach we take, and I should really stress, this is not something peculiar to Mathlib. This is something that has been used in proof assistance for a long time, is to rather use filters that were introduced by Bourbaki in the end of the 40s, beginning of the 50s. So it's a long tradition. And so, but nevertheless, unfortunately, they're not very well known. So I'll start with a brief introduction to what filters are. So, well, a filter is a collection of sets in your ambient. So you suppose you're given an ambient space, which can be a space, or for the time being can just be a set. So a filter will of course be a type in our framework, and a filter on this type is a collection of sets of this type. Pretty much like a topology is a collection of sets, and pretty much as a topology, it must satisfy some conditions. And so in particular, it should satisfy these three conditions. So the first condition is that the universal set, the whole type, must be an element of your collection. Likewise for the topology, the whole space is always open. The second condition, well, let me start with the third condition, which is easier. Third condition is that your collection must be stable by finite intersections. Of course, there will be examples in a while. So if you have never seen filters, I will provide a couple of examples, actually three. But okay, the first and the third conditions are exactly the same as things that you would ask to open sets in topology. So the third one is that F is stable by finite intersections. And the second one is that they must be upwards closed, meaning that if you have a set in your collection, and then every superset of it is again in the collection. So everything that contains something in the collection is again in the collection. So such a collection we call a filter. And this is the way you define filters in Mathlib. So you say it's a structure, which, as we have seen, structure is a way of saying, well, we are bundling things together. We are defining an object in some way, and we are requiring that this object satisfies some conditions. So as you see, a filter has 4 components. The first component is really the collection that you are given, and the other 3 are properties. So this is what is called a mixin sometimes. So there is a data, a collection of things, yes?
When you write a collection of sets in alpha, do you mean subsets of alpha?
Well, this is a very good question. The point is alpha itself is a type, it's not a set. So there is not a notion of a subset for a type. Set is the way, so set alpha, you can pretty much think of it as being the collection of all subsets of alpha. So for somewhat technical reasons, since alpha is not a set, I cannot say that something is a subset of alpha. But set alpha is the collection of basically of all subsets of alpha.
So if alpha, the real
numbers, set of alpha is the collection of all subsets of the reals, basically. Univ is the way of saying I look at the whole type as being a set. So sets and type are somewhat different. There is a way of speaking about sets, and the set is very easy to define. Actually, a set is a function from your type to prop. Basically, if you think as prop as being 0, 1, it's the characteristic function of the set. Okay?
And so we can see that UNIF, in my example, would be
the real numbers.
For alpha in general, but it is really not.
Exactly. It's not really alpha itself, because alpha is a type, whereas univ is a set. But basically, from the mathematical perspective, univ is the whole set. So univ of R is R. Okay? As a set is the set of all real numbers. Just that R in lean is a type, and the set of all real numbers is a set. So they cannot really be, strictly speaking, equal, but it's the same thing. Right, and so these 3 are the conditions. So for instance, the last one is that if you're given 2 sets in alpha, so 2 subsets, if the first is in the collection, and the second is the collection that you're requiring, then the intersection is the collection, and so on. Okay, so let's see some examples of filters. So the first thing you can do, for the time being, alpha is not really a topological space. Yeah, of course, you can think of it as being a topological space, but what I'm saying here is general for any type. You can give yourself a term in alpha, and then you can consider the collection of all sets that contain A. Well, it's easy to check. Well, the universal set will certainly contain A. If two things contain A, their intersection contain A. And if something contains A, then every superset of it still contains A. So the three properties of being a filter are satisfied. So the collection of all sets containing 0 or containing pi or containing 7 as a natural number, this is a filter. And more generally, if S is any set, well, the collection of all sets containing S is again a filter for exactly the same reason. So the example I gave before was just an example of a singleton, but it's the same thing. The second thing you can do, and is very, very useful and very much used in the library, is to look at the collection. Suppose that you have an order on alpha. So for instance, think that alpha is the natural numbers or the real numbers. Then what you can do is to consider all sets that contain each element from a certain bound onwards. But the bound is not fixed. If I consider all natural numbers that are larger than 10, well, this is a honest set. All the natural numbers are larger than 10. What I can look at rather is all sets that are larger than something which might depend on the set. So in other words, arbitrarily large sets. Well, now, again, it is a filter. Why? Well, first of all, the collection of all natural numbers contains everything above 0, so it satisfies the property. If you have two things that contain every element beyond a certain point, well, their intersection will contain every element beyond the maximum of the two bounds. And if you have two sets, and then if you have a set that contains everything from a certain bound onwards, every superset will always contain everything which is from a certain bound onwards. So typically, if you consider all numbers, like all prime numbers up to 100, and then all the rest, well, this will not be the whole set of natural numbers, but since from 100 and on you are considering everything, then this is a filter. And we will see in a while why this is very useful. It's a very useful filter. It's called at top. And it exists, again, for every order type. So for every type which is endowed with an order structure. And the third, and probably most likely to be the most useful application, well, the definition, well, case where you want to consider filter is if you're given a topological space, then you can do slightly different things from the one I did at the beginning, which is considering all neighborhoods. And by neighborhood here, I mean something that contains an open neighborhood of a point, of your given point. So why am I asking for all neighborhoods? Well, for the good reason that if something contains an open that contains your point, well, these big things might not be open anymore. It might be a closed that contains an open. But since you need to be a filter that things are upwards closed, well, you cannot do better than this. But indeed, if you consider all neighborhoods of a point, so all sets containing an open set containing a point, so you need a topology to speak about open sets, well, this will satisfy the property. So the whole space is open and it contains everything. The intersection of two opens that contain something is again an open containing something, and if something contains an open, well, it's something that contains an open contains your point. Okay, so these are the definitions. And for this, we have a special notation, which is n mathcal n of X, the neighborhoods of X. Now let's see, okay, all these might seem nice. Let's see why they're useful. So why are we using filters? And well, the reason is that, well, there are many reasons. They are really ubiquitous in the library. You find filters I would say almost everywhere in the library, and almost everywhere is a filter, by the way, but they are very useful to speak about convergence. So what I want to do is to, first of all, try to restate the usual notion of a limit, so the statement that the function converges to a point where the variable goes somewhere in terms of filters. And then we will see why they're useful. So why this reformulation is actually more suited for formalization. So the usual notion for, say, you have function from the reals to the reals, so you have two numbers, and you want to say that the limit when x goes to a of f is b. And then, well, this is the usual epsilon and delta definition. And then, of course, you can translate it by reversing, well, here actually using f backwards. So it means that for every epsilon there exists a delta such that the ball of radius delta around A is sent through f to the ball of radius epsilon around B. That's the usual definition we have. And now, well, you can try to be slightly fancier, say, well, what is the ball of radius epsilon around B? Well, this is a neighborhood of B, is what just we've said, because it's an open containing B. And likewise, this thing here is a neighborhood of A. It's an open set containing A. So what I've written here is that for every U, which is a neighborhood of B, there exists a neighborhood of A that is contained in the preimage of UB by F. For the time being, I haven't done anything. I've just translated the usual classical definition of limit in terms of epsilon and delta, just observing that well, all this delta and epsilon business is just a way of speaking of a ball around the point, an open ball around the point. And now comes the good news, is that this condition here, that VA is contained in the preimage, is exactly the same thing as asking that F minus 1 of UB belongs to this collection of set. Because since filters are upwards closed, this filter N of A, the filter of neighborhoods, well, it certainly contains VA, because VA, it is an open itself. And so it contains everything which is a superset of it. So what I can do, I can restate the condition that X goes to A, F goes to B as X goes to A in these terms. That for every U, which is a set, and it is an open, well, a neighborhood in B, then the preimage is a neighborhood of A. And this will turn out to be the crucial connection between filters and limits. And so the statement, for instance, that S goes to infinity, that F goes to B as X goes to infinity, becomes this very simple statement, that for every element, for every set which is in this neighborhood filter of B, the preimage is in the filter at infinity. Okay, so why is it useful? And now I will remind yourself a little bit how, so typically the proof, well, we usually prove in first year or something that there are good properties of limits. For instance, that if you take the composition of two functions and you know that the first function goes to B as X goes to A and the second function goes to C as the variable goes to B, then the composition goes to C as the variable goes to A. That's very easy. Then you start your epsilon and delta, you use the max or the mean or whatever, and you get to the proof. It's very easy to do. But then you realize that this other property, which is pretty much the same, the difference being that here A was a real number, and here the limit is taken as X goes to infinity. Well, this actually is not the same theorem, because infinity is not an element of the real numbers. So if I try to already state these result in these terms, well, it wouldn't type check in a sense, because plus infinity is not a real number. So what we do, well, we change the proof a little bit. Instead of taking epsilon and delta, we take epsilon and a capital N, and we say, oh, for every X larger than N, and something, blah, blah, blah. Okay, good. It's already, in principle, it's already a second proof, because there are two different statements, and so they have two different proofs. And then there's another thing you can do. For instance, you can go to A, but only from the left. And so you can say that if the limit for X going to the A from the left of something is, for instance, minus infinity, which is another statement, because here B was a real number, here B is not a real number anymore, and then the composition goes nice. And so if you try, there are at least 125 such theorems. And in proof assistant, it means there are at least 125 proofs. You start with the first, then you do the second, you do the third, and you go on. Of course, this is not what we do with people. With people, we hand wave and we convince them that we have proven this a couple of times, then it will most likely be true. But this is not really proving stuff. Huh? So this is certainly something you don't want in a proof assistant, even because in all these I have not considered products and exponents and all the business, all the disgusting stuff you can perform on functions and then try to state something about limits. So the great news is all these gets much easier when you use filters. So recall that I introduced this P of S, which was a set of all sets containing a given set. Now, what I'm going to do here, and then I will finish and I will switch to VS Code and try to do some live coding directly to show how to use filters concretely in Lean, is to try to convince you that this statement about the fact that we had been able to translate convergence and limits in terms of filters will allow us to give much shorter, much more conceptual and much more efficient proofs of these kinds of results, like the composition of limits is of some kind. So the first thing, what I need to do is generalize a little bit of a couple of things we normally use for sets to extend them through filters. And the idea really, what you should think, well, you think whatever you want, but what I would advise you to think is that in a sense, filters are generalized sets. So we had this way of giving a set, attaching to it P of S, the principal filter around S. And so in a sense, each time we have a set, we can cook up a filter. And the point is that there are many more filters than sets. There are all those filters that come from sets, and then there are new filters, new other ones. So in this sense, they are a generalized version of sets. But then we want to extend some properties, especially two key properties, which are the order property between sets and the push forward operation. We want to extend it to filters. So when you have two sets, S1 and S2, well, this is the same thing as saying that for every T which contains S2, T also contains S1. This is meaning that S2 is larger than S1, is equivalent to say that every set that contains the larger one also contains the smallest one. And so we extend the definition, this order, which we have on sets, we extend it to filter. And we said that two filters satisfy this inequality if the same property hold. Each time something is in the larger one, then it is also in the smaller one. And the second thing we extend is the push forward or something through a function. If you have a function from alpha to beta and you have a set in alpha, you can consider its image, which is a set in beta. And you do exactly the same for filters. You can very easily extend the definition of maps to filter. So with all these, the statement that as x goes to A, f goes to L becomes just this very sleek, very elegant statement that you have your function f from alpha to beta, you have a filter in alpha, a filter in beta, which you might think in this case f to be the filter neighborhood around A and G to be the filter neighborhood around L. And then the condition, as we have seen before, the condition that this tends to something was just this thing here, that for every set, that for every set, if the set is in the in this filter, then its pre-image is in the other one. Well, given our convention, it just becomes this. That once you map your filter and of neighborhoods around A through your function, you get something which is less or equal than the neighborhood around the limit point. So of course this takes a while to get used to it. We know what filters are, we know what limits are, we know what convergence is, and it takes a little bit to get used to it. But the point is that I'm trying to make, it's really just a dictionary. There's very little new mathematical information in it. It's just a more compact, more unified, perhaps more elegant way of discussing of something that we already know very well. So, yeah. So I'd like to try to, do you hear me? Now do you, now? Yes, okay, good. Okay, let's try to do some lean. Okay, so the first thing, so basically what I'm doing here are, what time should I stop, Marco? Well, when I have to stop, I'll shut down. I'll shut down at a certain point. Okay, so what I want to do now is to prove some, well, first of all, really show you how this composition of limits becomes nicer and neater using this language. And in general, doing a little bit of getting our hands dirty using filters and these notions that I've just introduced. So the first example I'd like to prove is that, well, this goal, you'd rather see it, read it on the right rather than on the left. So I'm giving myself a function from alpha to beta. Alpha and beta are two types. I have a filter in alpha and a function from alpha to beta, and I suppose that f is less or equal than g. So perhaps now you have forgotten what it means. I will remind you in a minute. And I want to show that the push forward of the filter f
is less or equal than the push forward of the filter G. So that's why I called my lemma mono. It's a monotonicity statement. Basically, any function, if you look here, you see that there is no assumption whatsoever on F, on alpha, on beta, on F, on G. It's a complete general set theoretical statement. The push forward function is monotone. So it respects the order. Let's see why. So first of all, we have probably forgotten what the definition of being less or equal was. So we want to prove that this inequality. Let's see. Let's see what this definition was. This definition was this one. Recall it was a generalization of the idea of two sets being contained one into the other. What does it mean that S1 is contained in S2? It means that everything containing S2 also contains S1. And so this is what I want to prove, that for every set that is in my beta, it's if this preimage is in G, then this preimage is in F, which is this inclusion. Okay, so as usual, if you have a for all statement, you can start with an intro S. So S is my set. And now I have an assumption, which is that F minus 1 of S belongs to G. Let's introduce also this assumption, HS. Okay, and now I need to prove that something belongs to F. I don't have much at my disposal, so I can have a look at all these assumptions, all these hypotheses, and the key one. At a certain point, I will need to use that F is less or equal than G. And let's try to remember, what does it mean that F is less or equal than G? Well, it means that every set in G belongs to F. So the conclusion of these is if blah blah blah, then something belongs to F. This is exactly what I want. I want that something belongs to F at the end, so I can try to apply this H and see where it leads me. Well, it leads me to the proof that F minus 1 of S is in G, which I'm lucky enough is exactly HS. Okay, I've proven it. Now, let me do one. Let me golf this proof a little bit, and for one reason. First of all, what do I mean by golfing the proof? It means make it shorter. And the reason why sometimes we try to make proof shorter is because the fact that you can really reduce a proof a lot is often a sign that there is nothing going on from the mathematical point of view. Of course, this can be pushed a little bit to the extreme, but as a rule of thumb, I would say that here, you see, I've used nothing. There was no assumption on F, there was no assumption on the capital. So it cannot be a hard proof because basically I've unfolded the definition. So the first thing I can realize is that, okay, at the very beginning, I told you we don't recall what this definition of filter of inequality is, but Lean knows it. So it's completely useless to tell Lean what it was. It already knew. And the second observation is that when I was here, I wanted to prove a conclusion. I observed that among my assumption, there was an implication. So I applied the implication, and then I realized that not only had I the implication, but I also had the proof of the premise of this implication. So there's no reason to split these into things. Oops. There's no reason, to split these into things. Okay. And let me even golf it slightly more, once more, because I really want to convince you that nothing is going on. So what is this inequality? Well, this inequality, I told you, is the fact that if a set belongs to G, then this set also belongs to F of F. Okay, so this is an implication, right? And as you've seen, we write implications in Lean using arrows. So this is actually a function. What I'm trying to define here is a function that takes a proof that a set belongs to this filter and restitutes a proof that the set belongs to this filter. And how do you define a function? Well, a function, you define it by taking a term and then deciding where you are sending the term. So this is the function that takes a term and sends it to another term. So, and then by exactly, you really done it. This is the proof. Nothing is going on. No, I can't. I know what you want me to do. I can't. You are annoyed, I know. But no, I can't. Well, I can show you here. Okay, so this is it. It is. So nothing is really going on. Okay, so now let's move on because I tried to tell you that all this was very useful if you want to speak about limits. So this was the definition I gave you 5 minutes ago on the slide, that a function tends to the filter G, from alpha to beta, tends to the filter G along a filter F when this is true. When the push forward of your filter through F is less or equal than G. These I hope, well, of course, all these is in the repo, so if you want, you can go there and have a look. But I hope I try to convince you that this is really equivalent to our usual epsilon and delta definition of limits and so on. So what I want to do now is try to prove, well, the composition of limits. So that now I'm giving myself two functions from alpha to beta and from beta to gamma. I have three filters of one in alpha, one in beta, one in gamma. And suppose that S goes to G along F. I suppose that T goes to H along G. And I want to prove is that the composition T composed with F goes to H along F, which is exactly the generalization in terms of filters of the usual statement. But beware that here, there is no problem in saying, I'm not committing to choosing that F or G or H is the neighborhood of a special point, is the at top filter, is the out bot, which is the filter for x going to minus infinity, or these kind of things. Okay, so how do you prove this? Well, first of all, as before, we have probably forgotten what the definition of tends to is. And tends to was really this inequality. So we want to prove that this function T composed with X converges to H along F, and the definition is just an inequality. So let me turn it into an inequality. Okay. Now I want to prove that well, this inequality is true, and I have to look among my assumptions. And well, all these are not real assumptions. These are just some data. So these are the only two things that have some mathematical content here. So perhaps since they also involve some tends to, let's rewrite tends to at these 2 points as well. So this will allow me to introduce one small piece of syntax. I don't know if you have already seen it. You can rewrite at several things at the same time, writing at and then a list of places where you're rewriting, but I also want to rewrite at the goal. So here I've changed my tends to into some more explicit things all over the places. Okay, now I want to prove that something is less or equal than H, and I know that something else is less or equal than H. So with some luck, I can use transitivity of the less than equal property and say, well, if these happens to be less or equal than the left-hand side, well, then I can chain to inequalities and I win. So I can try to apply a transitivity properties, transitivity property, and indeed I end up with 3 goals, which is reasonable. Now, I wanted to prove something of the form A is less or equal than C, going through an A is less or equal than B and B is less or equal than C, but I've not told the Lean what is B. So there's no way it can come up with the idea of B. There might be many choices for B or something. For the time being, I've just told him, well, I want A less or equal than C, and I will go through a transitivity property. Okay, fine. And then I have to provide, which is this intermediate step here, which is exactly the second one. So what I want to use was this HT. You remember, I told you that I wanted to prove this inequality, and I go through this inequality. Okay, so I can try to do HT. It complains, and rightly so, because actually, so I had A less or equal than B, B is less or equal than C, and this is what I had. So it turns out that this is the right way of doing it. Okay, so you have, to get A less or equal than C, you need to combine 2 inequalities, S or less or equal than B, which is the first one, and B is less or equal than C, which is the second one, and what I had, which is HT, is the second one. Okay, and now I need to prove that, well, this inequality. Well, but this I can restate. What is the push forward or my filter through the composition of 2 functions? Well, this is T is the push forward along phi of the push forward along S of F. So this thing here, you can rewrite it as map T of map SG is less or equal than map TG. So this is really, what I'm just saying is that the push forward through a composition is the composition through the push forward. So I can apply my monotonicity statement. What I want to use here is that T is a monotone function and therefore basically transforms this inequality into a map of TSF is less or equal than map of TG, which is what I have. So I can apply mono and I get an error. And it's fine. One thing that one has to learn while doing lean is that typically you type something and you get an error. And it's fine. You have to live with the error and try to understand the error, because the error message sometimes contains useful, very often contains useful information. Let's try to have a look at inspect this error message. In this error message, there are several question marks that shows off. And why do they show off? Well, they show off because this means that lean has not been able to understand what was the function f that I was speaking about. Okay, so we can provide it for it. Okay. We still got an error, not a problem. We still go and have a look. And now we see that the question mark is on this M47. So let's forget why it's called M and why it's 47. Damiano will explain the M. I'm not sure he will explain the 47. But the point here is that lean is missing, let's have a look, this inequality information. And this inequality is exactly HS. So what I'm applying here is this inequality. And you see, I've proven the theorem. Okay, so again, here I could certainly remove this line, which plays no role, and the rest can be golfed a little bit. And now let me show you that you can very efficiently use this to prove something. So the first thing, I want to go back to our statement, and I suppose that f and g now are functions from R to R, and I suppose that f goes to pi as x goes to 0, and g goes to infinity as x goes to pi. I want to look at the composition. I want to say the composition goes to infinity as x goes to 0. Well, I apply my tends to comp, and then, well, it requires the two limit conditions that are hf and hg, and it is a happy. So I proved this statement. It's very general statement. It has nothing to do with topological spaces, and now I can prove these. But on the other hand, in exactly the same vein, what I can do is I can prove that if I have a function, so if I have a sequence of real numbers indexed by the natural, and I see that when n goes to infinity, the first goes to -1, and then I function from the reals to the complex numbers. And can you imagine, if you really want to prove these in full generalities, this is not and you've just proven your epsilon and delta function. This is a function that doesn't, this is a context that doesn't fit at all into what you would really prove, because now the domains are different, and N and R and C are different, and there are a plus, and there's an I here. But again, you can just apply your tends to comp to these two assumptions, HA and HV. Okay, and it's proven. So in just the proof was very easy. One line again, and then everything is combined. And so we've got all these 125 plus proofs in just a couple of lines, because there's nothing going on. Now, let me finish. So as Marco told me, I only had 5 minutes left. So let me finish with one small tactic, which is very, well, it's not small, it's it's an extremely useful tactic. It's not very complicated, but it's very useful. So what we have seen is when you want to prove results about filter, basically they all spin around the idea of proving that some set belongs to a filter under given conditions. So suppose that we are in the following setup where we have alpha, which is topological space, and we have 4 properties on alpha, P, P prime, Q, and Q prime. Like, you can think of them like being inequalities. Perhaps alpha can be R2, and these can be inequalities, like, oh, x is less or equal than y, and these properties, x squared is less or equal than the exponential of y, and this might be something like x is equal to 7. The properties on R2, properties on pair of real numbers. Well, each property defines a subset of R2, and now you want to prove that these combination here, which is a union of intersection, is still a neighborhood, knowing that all these are neighborhoods. Well, this is mathematically trivial. I'm just saying, well, if I intersect things that are neighborhoods, still neighborhood. If I take the union of neighborhoods, still a neighborhood. That's all fine. But it's painful to prove because you have to in a sense, cut these inequalities and the implication in small pieces and then try to reconstruct everything. But from the mathematical point of view, there's really nothing going on because we are trying to prove everything I've done so far is basically proving that something belongs to a filter from first principles. And there are three first principles. The universal set is always in a filter. The intersection of two sets in a filter is again in a filter. And a superset of something in a filter is in a filter. That's all I have at my disposal. So there is this nice tactic, which is called filter upwards. That does, well, first of all, as a first guess, it does nothing, well, it does something which is quite stupid. So it tries to apply these first principles, but since it has not been given anything, the only general first principle it can use is the fact that a universal set is always in the filter. So what is happening here is that, well, I want to prove that something is in a filter, and filter upwards is telling me, well, if you can prove that this set is the universal set, well, you win, because by assumption, the universal set is always in the filter. Okay, sure. The problem is that this might be true, but might not be true. It can be very well false. But on the other hand, I have all these assumptions. So I can instruct filter upwards to also use the other two conditions, the other two requirements for a filter, which are these assumptions. And now things start looking more reasonable. I need to prove that something satisfies the condition of being in this set, given some assumptions. Is most probably most likely to hold. And so these you can introduce A. Oh, this is pain. All these QA implies Q prime implies P. Well, it implies something trivial. Well, this is just a tautology. Okay. So what is it going on here? Well, what is going on is that if you, well, of course, I can prove something false. Well, I can try to prove something false, and I will not succeed. But if the result that my set is in the filter, which is typically what I want to achieve, follows from perhaps intricate but trivial combination of, well, a pair of, one thing is in a filter, another thing is in the filter, the intersection is the filter, and something is in the filter, that other creature is a superset, therefore also the other creatures in the superset. Well, all these trivial combinations, filter upwards can kill all of them. And I will just finish mentioning one thing. I will not have time to do the example. All these is, of course, in the repo, and I'll be very happy if you want to download it and try it yourself to discuss with you later on. But just to mention that the filter library is also very, very useful if you want to speak about measure and measure spaces in particular, because once you have a measure, for instance, the Lebesgue measure on the real numbers, the almost everywhere notion related to this measure gives you a filter, namely the filter that we call co-null, whose complement has null measure with respect to your measure. And so with this language, you can state, but with this time constraint, you cannot prove, that if two functions, f and g, are almost everywhere equal on the real numbers, and if f, g, and h are almost everywhere equal with respect to the Lebesgue measure on the real number, then f and h are also almost everywhere equal. But I cheated. I will comment if I write filter upwards. Well, if two functions are equal everywhere, they're in particular equal almost everywhere. But if you add these h1 and h2 conditions, and then you can prove it in one line. Okay, so all the language of filter allows you, rather than going to, oh, if f and h, I should look at the complement of the places where f and g are equal and try to relate this complement to the complement of where f and g and grh are equal. These are null sets. Then I am intersecting them in a certain way. They still have measure 0. This would be painful, and this is, I think, sleek and neat. But I think I'm at the very end, and so I'll stop here. Thank you.
Okay, questions for Filippo? Yes. Can you wait for the mic?
Thank you very much for the talk. It's been very nice. I had a question when you were talking about examples of filters, the one in topological spaces. You have like pointed at technicity that it is not open neighbors, but neighbors containing open neighbors. I guess this definition is more convenient somewhere. Do you know where, because perhaps it could be also defined in terms of open neighbors, where is it more convenient to make this technical distinction?
No, the point is that if you require, the collection of all opens containing a point, this is certainly a collection you can consider, but it does not satisfy the second condition, sets of superset. Because if you take, if you have an open that contains a point, and now you have something that contains this open, well, this something might not be open anymore. Okay, so you have the problem that there are things, it would be very nice if I can consider the collection of all open neighbors, which I can consider, but it does not satisfy this problem. As you have seen, it is really important that this upwards closeness is very, very handy, very useful. It is a thing that makes things work properly and nicely. So you have to enforce it. But on the other hand, this put too much constraint on your collections, so as that you cannot consider just the collections. In a sense, you have to saturate. One way of producing a filter is starting with a collection and then saturating it with respect to the conditions that are required but that are imposed. And when you saturate the collection of all open neighborhoods by the property of being upwards closed, well, then you get something larger than just the collections of opens.
Okay, thank you very much.